So we have a number of things today. I'm going to briefly go back to the start and revisit what happened after the Australian heavy rains that we talked about earlier. And it's interesting how it's related to the typhoon pairs in the Western Pacific in there. So that has some implications of what's going on. So we'll start there. All right. So if we look at let's see, Alicia's map and
you're on that. On the projector or?
Oh. Okay. All right. If we first look at Heather Archibald's archive, going back, remember we talked about this disturbance that sat over northeastern Australia, which is very interesting for quite the extended period of time. This is back on the 5th of, if you go back to the 1st of February, this feature up here, this is the second, 12th was that basically land came that was over Australia. It had a lot of tropical characteristics. And it basically, if we go back to the 1st, 00Z on the 1st, it sat there for days and days and was associated with an incredible amount of flooding over parts of northeastern Australia in very unpopulated areas. So it didn't get a lot of press. But this was a 2-week rainstorm of epic proportions. And so the critters, the snakes and all that, the scorpions and all that, must have had a wonderful time floating down various streams into places where nobody wanted them to be. So that sat there, but we never discussed what happened subsequently to this thing. And as it approaches the coast, and that's when we finished up the previous discussion, it goes out to the east, and it turns out it becomes the seed for Oma, or however you say it, O-M-A. We're debating, how do you say it? Is it Ama? Long O, short O? But anyway, O-M-A, and not Om. So you can see it acquires tropical characteristics out there to the east. There's a contour 582 thickness in here, a circular, nice configuration, characteristic of a tropical cyclone. Now, if we zoom out and look at that at a somewhat different perspective from Alicia's maps, which are here. Oops, I have to go to Australia. All right. If we look at Australia, and this is today. All right, but let's back up in here, and so that's Oma sitting right here. And if we back up, note what had happened. Going in reverse, 19th now, 18th February. You can see it's been slowly moving out there. These islands out here, it's been just to the west, there's been strong northerly flow to the west of these islands for quite a while. I don't know if any rain gauges are on those islands or whatever, but it's got to be an awful lot of rain going on there. But you can see we're now back to the 13th of February. I'm going to get back there. You can see where it originates from. See? Back to see over northeast Australia. This is as far back as Alicia's maps go. But that's the feature that on the 8th that was over northeastern Australia for almost 2 weeks in the rain. And it now will go forward. It edges eastward. Note there are other little tropical-like systems that are sitting out there as the MJO convection moved eastward. So there it's moving eastward. Now it's doing Fujiwara. Remember, this is the southern hemisphere, so it goes the other direction, clockwise around there. So they're playing ring around the Losey, and it stalled in that region. Awful lot of rain. So the question then becomes, you go into forecast mode here, is will a trough from the southern hemisphere pick up, south of Australia, pick up Oma in through here? Like, it's been very hot, very, very hot summer. Australia had its hottest month they had on record was January of this year. Never been a hotter month in Australia. But you can see there's this trough that comes in through here, past New Zealand to the north. It tries to pick it up in the deterministic run, it doesn't. But in some of the other runs, there are some members that pick it up. But see, in that run, the deterministic run, it's still sitting there. And what's interesting is it's slowly moving westward and weakening back towards northeast Australia, back to where it started from. So this is a remarkable long-lived system with an antecedent formation over land, very slow moving, became a TC over the water, and now it's weakening and heading back towards where it started. So, long-lived odyssey, worth studying. So, how, if we look at now at the bigger picture, and Ming Hao, you want to come up and talk about the paired cyclones, tropical cyclones, and what some of the implications of that. Take over.
Yeah, do you want to switch? So
You want to switch the computer?
Yeah.
Okay. Over here. So which one is it on, Danny? You're on 15?
Yeah, 15 and 16.
Oh, no, 15 on that. Here's your cursor.
So, if you go to, thanks for Philip's tweet. Philip made a very nice animation and explanation of how the MJO propagation and these twine TCs along the equator form. So if you play the video, so you can see that as your MJO propagates from west to east, from the maritime continent to the eastern Pacific, there's a dynamic response with that you have the westerly wind burst along the equator, and he argued that there was some sort of equatorial Rossby wave coupled with that, and that spawned these two TCs simultaneously. And some of the outflow of the tropical cyclones may help enhance the mid-latitude jet and further influence the weather patterns downstream. So we can play it again. So it all started from 2 weeks ago when you have
that enhanced convection is what we were talking about. That was over in northern Australia originally.
the active MJO convection, westerly wind burst, and the dynamic with response. It spawned both cyclones on both hemisphere, and they pay their row, move to the west. And if you go back and look at one of Philip's latest tweets, he argued that the cyclone genesis of these two tropical cyclones may be a collective response of three signals acting at the same time. One is the low frequency ENSO signal, and one is the eastward propagating MJO, and one is the equatorial Rossby wave. And this is showing the half-model of the velocity potential. When these three signals come together at the same time, that's around when these cyclones get started. So I think that's a very nice way to see, especially in northern hemisphere, only in wintertime, in very low latitudes, you can have these twine TCs on both sides of the equator. So Nance just talked about Cyclone Oma in the southern hemisphere, while in the northern hemisphere, Typhoon Wutip was officially the third most intense tropical cyclone ever in the western North Pacific in February. I think the central pressure got down to 955 hectopascal, and it was upgraded to category 3 last night. And in terms of the latest forecast, if you click on the storm info and look at the GFS ensemble on the Tropical Tidbits webpage, so we were kind of wondering how Typhoon Wutip will check afterwards and whether it will recurve. That will have some implications on its extratropical transition or downstream impacts. So from the, I think this is a 12Z GFS ensemble, some of the members have Wutip to recurve, while the other members have it to slowly moving towards the north and then weakens and refuse to recurve after that. And some of the members that recurve have stronger intensity and moves faster than these members that don't recurve. And while at the same time, if you go to the EPS ensemble, there are more ensemble members from the European forecast that did not recurve. More members were having Typhoon Wu-tip to go north, and then it stops there for a while and tracks westward. And one possible reason for that is as it goes above perhaps 10 degrees north, the sea surface temperature decreases pretty rapidly. It's like 28 degrees C here, but only 26 or 25 degrees C here. And it's forecasted to weaken pretty fast over the cold water as well as the dry air intruding from the north. So before it was able to interact with the westerlies, its circulation just shallows down and weakens and being steered by the low-level easterly wind and then tracks westward. There's a discrepancy in the JFS ensemble forecast and the EC ensemble forecast. But we might believe that it may more probably not recurve at this point. So it might have limited influence on the downstream flow patterns later on. From the earlier European forecast, in the next 10 days, they're still blocking India, Alaska, and troughing on the west coast, which will continue for a while.
Yeah, but it is, one of the interesting things here on this is this point here. So this is a critical point where a lot go this way and some go this way. And what I find also interesting, you have a few that clearly recur, but even the ones that go this way, there are one or two that recur. So what's the difference between these two that recur here versus over here in terms of the evolution? How important is what happens here from the predictability point of view in determining the spread that goes this way? And then of the ones that go this way, what governs a couple that actually recur? I mean, the downstream impacts are going to be huge. If this scenario verifies, it's going to be a big difference than if that scenario verifies or this scenario verifies.
Yeah, actually, if we go to
Jeremy has a, yeah.
Well, I was just going to say that this is very reminiscent of the cases that Travis looked at. He was looking at PCW over the Gulf of Mexico and had this kind of bifurcation point in which the ensemble had tracks going one way or the other. And they actually recently published a paper with Ryan in which they looked at a number of cases. And they found that typically when you have this pattern, there's a saddle point at that location.
Yeah.
Where there's two different flow regimes that are connected. So it's really sensitive to TC track when it gets right to that point. If it goes one way, then it gets just shut it off into that direction or the other way. So this is like a very classic example. They also looked at a typhoon over the West Pacific. I forget the name of it. So I would look back at that paper to see if some of the flow regimes are.
Reasons for that bifurcation point. Yeah, just go to the Western Pacific view. Western Pacific. And go to 200 millibar wind. Yeah. Yeah, same. So that bifurcation point is when, I think there are two jet cores in the westerlies. When the first one failed to pick it up, it would just refuse to recurve and wait till the second one to pick it up. So there are like separate cores of the jet streak. If the first one does not pick it up, it will not recurve, while the second one might pick it up afterwards.
Yeah, I was also kind of wondering, it would be interesting to look at all of the EC ensemble tracks. I'm not saying we should do this, and separate them by the TC's intensity at the bifurcation point, because sometimes you have different steering flows based on how tall the PV tower is that's being steered by the mean wind. So sometimes the intensity can play a role in the bifurcation point, in addition to the change of differences in mean flow.
Right. There's definitely some difference between the members that recurve and those that don't. Either because of the steering flow or the depth of the storm, or interaction of both.
Yeah, I was going to add that this seems to have some similarities, at least similarly to what Ross was saying to, I think it was Hurricane Lane last year, that it also reached a similar bifurcation point where at least some members took it further north into the Big Island, whereas others kept it south end.
Right.
That seems to be largely dependent on the intensity. That I think some of the walls had some of these ensembles had it remaining fairly strong distribution wise, so I think the peaks are still fairly tall and kind of interacted more with the westerly flow lots, whereas it quickly weakened to the shear and dry air and then kind of just quickly steered to the west.
Right, I think we can see that from the GFS ensemble, that the stronger members were recurving, weaker ones were not recurving.
Yeah, so my.
Yeah, and also here, you have more red and blues here, while all green dots here. But typically in February, it's very difficult for the typhoons to recurve over the western North Pacific because the jet is just so strong and you're at the equatorial exit region, which is not favorable for interaction with tropical cyclones. Right. So Nancy, would you like to talk about the MJO forecast?
Yeah,
Or
you
we'll
guys
just
do
move
that.
on?
Go ahead, yeah, just briefly, go ahead.
Okay. Okay, so the MJO, as forecasted, did not amplify over phase 7 and 8 as what the GFS showed before, and it went as what the European model showed, and it's not in phase 8. And it's forecasted to be moving around across phase 1 and 2.
Tie back the heavy rain in Australia with a circular,
Oh, yeah.
yeah, right there, yeah.
Right, that's when you have those very active convective activities, very active IDCZs associated with the MJO when it's on the northeastern side of Australia, and when you have those cyclogenesis in the IDCZ. Yeah, but after that, the MJO propagates out of there. I think this is a cold phase for the central U.S.
And the eastern US.
and the eastern U.S.
Yeah.
It's coming towards us. And yeah.
We'll believe it when we see it.
Right, so next we're going to move to the western central U.S. and talk about the cold and snow in the southwest U.S.
Well, first, the revolution, Tyler's gonna take over the evolution of large-scale flow in the Pacific to set up the cold and snow.
Right.
So if you could pull up, yeah, Alicia's and Tomer's would be nice. And then if you just go back in time a little bit. So I just wanted to give a quick overview of the general synoptic pattern that we've seen over the North Pacific. For the most part, we've been locked in a pretty amplified flow pattern across the Pacific. We've had, a couple weeks ago, we had a very retracted jet across Eastern Asia, and with that you had large excursions of the polar jet northward, which we've seen repeatedly. So if you could, can you go back even further on Alicia's and Tomer's map? Yeah, so starting, what is this, Friday, February 8th. So like Lance was saying, as the convection was happening over northern Australia and the southern hemisphere, we hypothesized that the diabatic outflow would be able to concentrate the jet, so that was more retracted, and the subtropical jet was a bit stronger. And if we step forward, as we see the weakening of that, the jet does meander a little bit further out into the Pacific. But with that, we also see this persistent blocking pattern right here in the Eastern Pacific, right in the Gulf of Alaska. And that's kept, that's been just far enough off the coast. What is this? So this is just this past Monday, just far enough off coast that you get cold on the western coast of the US, because the trough can dip down onto the coast and it's not affected by the ridge itself. So if you keep going forward, you know, this is what we've seen with the snow in Seattle, snow getting down this morning even into the hills of Malibu. You know, really anomalous features there. What was it? I think it hasn't been since the 60s that they've recorded snow in and around LA. Am I getting that right?
Could be.
Maybe.
It's about at that elevation anyway.
Okay, yeah. So I think, yeah, freezing levels were down around
1,000 feet, I think.
yeah, 800 to 1,000. Really anomalous things, and that's associated with this really deep, almost cut-off low across the southwest U.S. So if you could switch to, let's see, maybe the dynamic tropopause. Yeah, you can really see that here. See this PD streamer sort of feature here, extending down all the way from Canada and coming down southwest towards the towards California and Arizona. If we step forward, we step forward, we see this continuous ridge building here in Alaska as just as these cyclones move through in the Pacific. If you could keep stepping forward, you see, you know, it dwindles down a little bit, then builds up again, this retrogressive ridge building, and it just is forecasted to continue like this quite a while, with this really amplified pattern in the North Pacific. And then Lance, I'll hand it off to you to talk about.
Okay, why don't you show the 500 vorticity first as it comes
Right.
into the trough? That won't do the change.
Right, so if we step back a little bit. So you see these, you know, this train of short waves progressing over the mean trough, or mean ridge in the area, and coming down on the other side. Right here, we see another one coming down along the Pacific coast. And yeah, it just keeps reinforcing this pattern. And it's not till later, if you want to step a little forward, that we actually get an even further excursion forward of the jet. And then with that, you get some undercutting, and you finally get some more typical zonal pattern for California, Arizona, Oregon, all along the West Coast, and a lot more, a little bit more climatological than having these deep cutoff lows in the area that have been so present. And then that was about it.
Okay.
Thanks, Tyler. Okay, so now we want to zoom in on this feature, which is going to be which is associated with the, that's the 28th. But let's go to the couple of days ago to see the cutoff that's leading to the all-time record of daily snowfall total of, I think, 35.9 inches fell in Flagstaff yesterday. That's not chicken feed.
You can also add redid my statistic on that, and it turns out there things for 5.9 inches. That's about more than 66% of the U.S. has seen so far this winter.
More than 66% of the U.S. has seen what?
This winter.
This winter. Yeah.
In one day.
Yeah, in one day. Certainly here. All right, so this is on 0Z the 21st, and if you do it like a deprived DT, you can see that the forecasts aren't bad. As Tyler pointed out, there's a series of wave trains in the.
Well, you want to bring up the T-prop DC on travel pivots?
Okay, Alicia's work would have worked just fine, but it doesn't matter.
Oh, that's true. She has
She's got, yeah. All right, let's take the Pacific view first to see as opposed to North America. Yeah. All right, so if we go yesterday when the heaviest snow, say at 18Z yesterday, we can put the North American view on the right side. The verification at 18Z yesterday was when first we could set it at. And Flagstaff at that time had 1/4 S plus, 1/4 mile S plus in there. So it's not very hard, but the effect of these, this is, let's see, 12Z today, right? So, all right, so let's go back to 18Z on the 21st. You can set the verification date on here, this one, the top one, 18Z yesterday.
Okay, yeah, there we go.
Yeah, there we go. Now we can do it. But the initialization date has to go back on the left here to as early as that's available, probably around the. All right, so that's the 14th. So if you look at the prog DT, so this is the 174-hour forecast verifying this time. Now we can step through and see overall that the forecasts aren't bad. There's jumping around where the trough is, but all the forecasts have the trough on the western and southwest part of the country into here. By the time you get down to the 3-day forecast, 72, you're really locked in. Remember, the blue is the areas where the strong ascent. So you can see the strong ascent coming right up into southern and central Arizona and southern Nevada in through here. And with this series that Chandra pointed out, that with this series of troughs that have just come down, and now it's gonna change a bit finally with the big ridge. With all this discontinuous ridge retrogression, it's just, this one goes down, this one comes up. We've seen this now so many days in a row, what's going on. So that's the feature in through here that was responsible for the event. Now you can look on the bigger view, if you look over here in North America, in through here, this is a classic recipe for a late winter and early spring major plains storm, when you have a deep trough out here in the southwest, flat ridge in the east, big 588 high contour down and through here. So this allows moisture from the eastern Pacific to get sucked in, and from the Gulf of Mexico and the western Caribbean, and this represents then a severe weather threat. As we go forward, we'll see that in through here, and Jenny will talk about that and others a little bit more. But the point is, I just want to leave it for now, is this kind of feature, when it comes out, causes all kinds of trouble. And we'll talk about that a little bit later. So the details of Flagstaff, if we look at where the air came from, and through here, calculate a couple of trajectories, back trajectories from using the NOAA high-split model. And let's see.
Do we have any predictions for that?
Where did they go? No, that's for the Uberjet.
Yeah, I don't know if, did you send the trajectories for Flagstaff?
Yeah.
Okay, I don't know if we got it.
No worries if not.
Yeah, we have it right now.
You got it? Okay.
Maybe
Might come back to them later.
3 minutes. Yes.
Okay. We'll do something else in the interim. One of the questions when you have the snow was what in Flagstaff. First of all, remember Flagstaff's at about 6,500 feet, so there's a strong orographic component of ascent to the lip that you have in Flagstaff. And where does the moisture come from? How much is generated in situ versus how much is, say, infected in from other regions? If we look at the IVT from Alicia, here we can take a look. Let's see. Oh, I guess we have the water. Yeah, there's the IVT. If you look at this, and this is go back a few days, if you would. So you can see some of the moisture is coming up and around, over. Keep going forward. Red vapor transport coming down along the west coast, and then entering into this region. At this stage, with the origin of these troughs coming down from this way, you're not seeing a lot of deep tropical moisture from the southeastern Pacific getting into this area. Most of this moisture came over the top, and then because of the deep trough, was able to turn the corner and come right up into Arizona, where orographic ascent, the snow to liquid water ratio, I guess in Flagstaff was about 25-1. So about 1.5 inches of liquid water compared to that a little over 2 times that amount of snow. So you're not dealing with a big source, and you can see that. Do you have the trajectory yet?
Where did you put it?
Flagstaff backward trajectory. There we go. All right, so this is ending at 500, 1,500, and 3,000 meters above the surface. There's Flagstaff. So you can see everything is coming down the coast. The green is ending up at 3,000 meters. It was near the surface 12 hours ago. Offshore came in at sea level and through here, and then strongly has ascended in the last 12 hours in through here. Similar with the red and blue trajectories ending at the surface at 5,000 meters and 1,500 meters. Strong from the continental source in here from the north, coming down and around. And then there's one other map, and I'll finish that up. We're looking a little higher. Okay, so is there any difference if we look a little bit higher? Not really. You can see the trajectories come in from the Gulf of Alaska and Alaska itself, and have an Asian origin over Northeast Asia in through here, come all the way across the Pacific, down and around. No tropical connection with this snowstorm at all. So it's all doing it on orographics and moisture that basically moved up and around, that may have had a tropical origin at one point in the Western Pacific, but moved up and around and over. All right, so that's enough on Flagstaff. So what's Rob's next, right?
Yep.
All right, Rob. Rob Pavel's got some interesting things to share us about the HER model boundary layer issues.
Okay. Matt, do you mind if I use my own laptop there? Can you help me get set up there?
Holler if you need help.
Is it just instant laptop?
That'll do it, yeah.
Okay, so it seems like there's every map discussion, there's some mention of the PBL, and usually in a disparaging way. And there's like 17 different PBL schemes in WRF, and they give different results. It seems that some should be maybe better than others, and it would be good if we maybe started trying to look at some of the details of these systematic or background characteristics of these schemes rather than looking on a case-by-case basis, which could be a little deceptive. So the goal of this is to assess systematic background strengths and weaknesses of PBL and surface layer schemes by exploiting underutilized data, that is the 1-second radio sound data, averaging forecasts over space and time to try to get back at the sort of like the background, mindful that and recognizing that the PBL scheme is not the only thing that's going on. If we see errors in the model or errors in the results, it's not necessarily just the PBL scheme, it could be other things, but perhaps suggesting some avenues for improvement. So the data sources I'm using for this are the high frequency radio sound data, 1-second resolution, so between 5 and 10 meters vertical resolution. The HER native model level analysis and forecast grids over a period from mid-December to the end of January, okay? These are not archived anywhere that I'm aware of, so I've been capturing them since December 18th and using that for this particular analysis. So I've got 2 model runs per day, 0Z and 12Z over a month and a half. That's 82 HER runs, 41 started at 0Z, 41 at 12Z. And just to remind you, the HER is WRF ARW, and it uses the MYNN2 PBL scheme. If you don't know what that means, you need to take my WRF class. So I've got data processed by the RRS decoder software provided by NOAA. This reads in the raw radio sound data. It spits out PTU and GPS files. PTU files are quality controlled, corrected and smoothed pressure, corrected temperature, relative humidity, and geopotential height above mean sea level. And the GPS files consists of geometric height above mean sea level and low pass filtered wind data to try to remove the pendular motion. And I also have 1-minute ASOS wind and gust information from NCEI. So although I want to show you the radio sound stuff, I want to actually start with the 10-meter winds to show you how good the HER 10-meter wind forecasts are. These are 850 plus ASOS stations for the CONUS that I have available during this particular period. Looks like a serious case of the measles or something. And these are the forecasts composited together over all 0Z and 12Z runs over this period. So each of these plots, the horizontal axis is forecast hour between 0 and 36 because the HER runs out to 36 hours. The vertical axis is network average wind speed, so that's averaging over those 851 ASOS stations. The red is always going to be observed and the black is forecasted. So we can see for the 0Z runs, we have a very close relationship between the observed and forecast 10-meter winds. We're averaging basically over all weather events. We're averaging across 4 time zones, and basically what's left is this diurnal variation. Actually, the largest bias is at the analysis time, and it's about a ½ meter per second too slow, but you can see that the bias is negative through most of the forecast period, but it gets actually smaller with time, okay? 12Z, similar story, starts off with a little bit of a negative bias, so that means the forecast winds are a little too slow, but it kind of catches up as a function of time. I think it's worth remembering that averaging over the network, these are very good forecasts, but there are systematic biases from place to place. Here what I've done is I have ranked with respect to average forecast wind bias at 10 meters averaged over all forecast hours for each individual station. So there are 851 dots on this diagram. I put them in rank order. There are stations that are systematically under forecast and systematically over forecast. This station, Guadalupe Pass, always sticks out as being really weird. I finally looked at it on a map that is not an airport station. It is actually a ASOS installation that appears to be poised at the edge of a cliff, okay, near El Paso, Texas. So basically that is not a 10-meter wind, okay? So, but otherwise, this is as close to a normal distribution as you're ever gonna see in messy meteorological data. So this is actually a pretty good result. So let me move on to the radiosondes. We have a lot fewer of them. We have 60. There were 61 before November, but San Diego dropped out, okay? And since about 1/3 of the NWS office in San Diego were my former students, I finally decided to ask them what the hell's going on. So if I figure out where those data went, I'll let you know.
Miami got lost also on here.
I don't know if they were ever there.
Key West is there.
Yeah.
And Vandenberg has a radiosonde station. They're not
Vandenberg
there.
has
Denver's
never
missing.
Yeah. Okay, so
Is this my next one?
yes. Okay, so what I need to do for boundary layer verification, I need to determine the height above local ground level, okay? But all of the data I get from the radiosondes are relative to mean sea level. I have 2 estimates of observation height, both above mean sea level from the radiosonde. Geopotential height derived from pressure, geometric height derived from the GPS, and unfortunately they can be very different near the surface, so I will touch upon that in a little bit. I have 3 heights for each station: the balloon release height, the barometer height, but I also determined station height because I couldn't find it anywhere else by using Google Earth to determine where these balloons were being launched and how far they were above sea level. So once I've converted the observations to above ground level, AGL, and I vertically interpolate them to the HER model levels for every radiosonde site and release time. The HER model levels actually vary in space and time because the WRF model uses a mass coordinate, and you remember the hypsometric equation that when the temperature goes up, the thickness increases. So actually the WRF vertical model grid sort of like goes up and down. I'm going to compare wind speed and dry bulb temperature, compute bias for each site and HER level, and then composite over all of those points. So let me quickly mention, so the HER model levels, the lowest model level is about 10 meters above local ground level, but actually that varies between 9 and 11 based on near surface temperature. The second model level is about 37, the third model level about 85, and the fourth model level is about 163 meters, but again it's varying with space and time based on conditions. So this is a plot of the height of the first model level for all stations over all times versus the temperature near the surface, and you can see as the temperature gets warmer, the model levels actually rise. So I have compensated or dealt with that by interpolating at every location at every time, okay? A more important thing, and I may not dwell on this too much, is I've got simulations at 0Z and 12Z. Each one is 36 hours. And so if I have a 24-hour forecast that is verifying at 0Z, that came from a 0Z run. But if my 12-hour forecast verifying at 0Z came from a 12Z run. So you'll see there's some variability from the 0Z runs to the 12Z runs with respect to the temperature error, okay? And this is where I think it's basically coming from. Okay, so let me demonstrate what this plot is to you. These are wind bias at 0 and 12Z, temperature bias at 0 and 12Z. So bias is the horizontal axis and the vertical axis is height. So each dot there is a HER model level averaged over all locations. So the lowest model level is about 10 meters, that's about 37, that's about 80 something, okay? And so these are averages over basically 41 simulations for each of these panels. So starting near the surface at 10 meters, the average analysis time forecast wind bias at 10 meters is minus 0.82 meters per second. That is relatively comparable to what I got from the ASOS network, which of course has 10 times as many stations, okay? But then at the second model level, about 37 meters above the ground, it swings more than a meter per second to a plus 0.32. That's not a large value, but this large swing in sign and magnitude is disturbing to me, okay? Then it kind of backs off and stays close to 0 as a function of height, which I think is a good thing because your analysis should really be your very best time, okay? Forecast skills should degrade in time. So I'm not so sure whether I'm handling the data from the radiosonde closest to the surface exactly correctly, and that may be part of this issue. Or it could be a problem with assumptions in the surface layer scheme, okay? But I can't tell the difference between those two yet, okay? But I think I have a way of mitigating this or making it at least irrelevant, so I'll just move on. So basically I have a negative bias near the ground, it swings to positive and then goes back close to 0. At 12Z, something very similar. Temperature bias, we start with a weak cold bias, it goes to a small positive bias and then it goes back to 0 with height. And at 12Z, it's even smaller in magnitude, but generally positive. So this is the analysis time, the average of all 0-hour forecasts. This is what the HER model is starting with. And then these are the forecasts, okay? These are color-coded so that cool to warm is increasing forecast lead time. So this is the 12-hour forecast, the 24 and the 36-hour forecast. We can see at 0Z, we quickly go from a bias that is close to 0 at the analysis time, which is good, to 3/4 of a meter per second bias at a maximum altitude of about 600 meters above ground level at 0Z. And so there's a big increase in the bias at 12Z, then there's a smaller incremental increases on top of that, the 24-hour forecast, and then the 36-hour forecast. So what we're starting with a wind profile that's probably pretty good, but it's quickly becoming biased positive at every altitude, and is growing with time, but the biggest change is in the first 12 hours, okay? That is also happening at 12Z, but the largest errors are closer to the surface, okay? For temperature, notice what's happening is we're starting with a bias at the analysis time that's close to 0, but it's quickly becoming more than 1/2 degree too warm close to the ground and about 1/2 degree too cold farther aloft, so that it represents a lapse rate that is more than 1K per kilometer too steep, okay? I think that's probably significant, okay? And that also happens at 12Z. In fact, the steepness of the lapse rate at 12Z is even higher. So I have 3 slides amongst here that I kind of want you to maybe take away from this, and this actually is one of the slides. So what I've done here is I have showing you the bias for wind and temperature at 0Z and 12Z, but I've subtracted off the initial analysis error. So that's arguing that if I'm making a mistake near the ground, why am I not making that same mistake at every possible forecast time? So I'm just going to emphasize how the bias changes from the analysis time. And so what we see here is that From 12 to 36 hours, the bias basically becomes large relatively quickly and then continues to grow. It's located relatively closer to the ground at 12Z than at 0Z. And here is our steepening of the lapse rate relative to analysis, okay? And by the way, I'll just show for the left column, that's what the water vapor looks like. There's not a lot of water vapor in the winter time, but basically there looks like a positive bias at 0Z and a negative bias at 12Z. So let me move on, okay? So here's another way of looking at it. I'm showing you profiles now instead of bias. This is wind speed at 0Z versus height, wind speed at 12Z versus height, but this is a log scale, and that's a linear scale, that's for temperature. So again, black is forecast and red is observation, okay? This is the analysis time, the 0-hour forecast. Except for very close to the ground, which again may be my not estimating the height relative to the ground correctly, that looks really good, okay? So the fact that the black and red curves are on top of each other is good. It's not quite as great at 12Z, but that's probably good enough for government work. And the temperatures also look pretty good too. But I'm gonna now move ahead to the 24-hour forecast. And let me flip back and forth a few times. First thing you may notice is that the red curves are not moving because that's the analysis. That's the average over all of the observations, okay? But we see at the 24-hour forecast, the winds are uniformly shifting towards higher values because we have a high wind bias in the HRR, averaged over the CONUS. That also happens at 12Z, but that's manifested mostly closer to the surface. And there is our temperature bias that comes from the lapse rate being too steep. Does that make sense? Okay, so this is the principal results that I have, but I want to make sure I am not fooling myself. So this is Richard Feynman wagging his finger at all of us, reminding us that you are the easiest person to fool, okay? So let's see if I'm making a mistake here somewhere. So our problem sites or observations contaminating these results. I mentioned from the radio sound, I have two estimates of height, and unfortunately they don't agree with each other. This is a launch from late December from Albany's roof. The vertical axis here is pressure, and that's what the black dots are. This is the first 30 seconds after the model launch. But during those 30 seconds, it rises up through 3 HRR model levels, okay? So the balloon sort of like has a slow start and then finally starts to ascend. This is, in red, is the height from the geopotential height derived from pressure. So the balloon starts to slowly rise. But in blue is the height of the balloon from the GPS instrument. It differs by 17 meters at the 11-second point. 17 meters near the ground is a huge difference when your vertical shear is so big. So this is the kind of thing that is worrying me about the lowest couple of model levels, okay? But I'm gonna ask the question, is it biasing my results? This is a plot of the height difference between the geopotential height and the geometric height from the pressure and the GPS, and that's the wind speed bias at the lowest HRR model level, and there's no relationship between those two at all, okay? Another issue here is that various places, although the HRR is a high resolution 4 kilometer, something like that, maybe it's 3 kilometer, I've forgotten at the moment, but although it is high resolution, it does not mean that the altitude of each balloon launch site is exactly correct. In fact, the average of the 60 stations, the HRR point is 8 meters too close to sea level, okay? And this is a plot in rank order of those 60 sites as far as the difference between the balloon height and the HRR model height, okay? So basically, 44 of the 60 stations are within 14 meters, but basically that's a distribution that looks like that. That shows up in the temperature bias, as you can guess, okay? So this is a plot of the elevation difference between the HRR and the actual radiosonde site, and this is the temperature error at the fourth model level, about 163 meters at the initial time. So if your station is a little too close to sea level, you're gonna have a positive temperature bias. And vice versa, if your station is actually in the models a little higher than actual, because temperature is such a large function of altitude above sea level, okay? So this may tell me I need to eliminate the stations that are too far away, the height discrepancies. But actually, since I'm gonna emphasize the change in bias with time, this is the change in bias to 36 hours versus the elevation difference, and there's no correlation, okay? I said there were 3 slides I want you to take away. This is the second one, okay? This is the change in temperature bias between the analysis time and 36 hours versus not the elevation error, but the elevation of the station. I arbitrarily drew a curve here at 500 meters above sea level. Above that point, 20 stations, every single one of them has a positive temperature bias. But below it, the average temperature bias is 0. So there is a big change between higher altitude and lower altitude stations that I have not yet figured out what it is. And it's not necessarily the boundary layer either. It may be something related to the land surface, the surface cover, the vegetation, the snow cover, the radiation, the cloud cover, or something else. But it's also possible that there's a bug in the model that has been uncovered by this analysis, okay? Here's another plot. I'm plotting the station pressure difference versus the difference or discrepancy between the model site elevation and the actual site, the actual launch elevation. So the horizontal axis here is the difference in elevation. This is where the model is closer to sea level than the actual site. And the vertical axis is the difference in the station pressure, and you can see there's a very close relationship there. The slope of this line is 120 millibars per kilometer, which is the DPVZ in the lower troposphere. Except these few points stick off. Tallahassee, Del Rio, Texas, Key West, Tucson, and the very worst one is this place called Albany, New York. Okay, so they not only launched the weather balloon off the roof, but their barometer is not near the surface like it's supposed to be, and we see that, okay? Okay. So let me quickly go through this. I only have a few slides left. What I've tried to do here is I've tried to remove all possible problem stations. I'm removing stations that if the discrepancy between the geopotential and the geometric height is too large. I'm removing sites that are above 500 meters above mean sea level. I've removed stations that launch the balloons off the rooftops like Albany, and that actually costs me half of all of my observations, but the results are practically identical. So I still have the wind increasing, the positive wind bias increasing with height. It's closer to the ground at 12Z. I'm still getting too warm, very close to the surface, and too cool near the top of the convective boundary layer. So in my last few slides, let me try to talk a little bit about how this error evolves over the first 12 forecast hours, and I'm back to using all 60 sites, okay? So this is wind speed bias at 0Z relative to analysis, so I've subtracted off the analysis time, and this is the 12-hour forecast. So for 0Z, it means it was started at 12Z the previous day. This is the bias relative to analysis time from the 15Z run, or the 9-hour forecast. This is the 6-hour forecast starting at 18Z. This is the 3-hour forecast from 21Z, the 2-hour forecast from 22Z, and the 1-hour forecast from 23Z. So 1 hour, 2 hour, 3, 6, 9, and 12-hour forecast. From that, that shows me that the wind speed bias near the surface starts in the first 60 minutes, okay? And basically about something like 70% of the error that is finally achieved through 36 hours appears in the first 12 hours. So there's something going on with the boundary layer scheme or the rest of the model, that when the model starts, it goes towards this positive bias very quickly. That tells me that when I want to investigate this further, I'm going to focus on the first 12 hours because that's where the root of the problem is. But this plot is telling me the temperature bias spins up more slowly, okay? And that is also true at 12Z, so these are the equivalent plots for 12Z. And I'll finish with this plot, which is a function of forecast hour. This is the growth of the wind error at 0Z from the 0Z run, the growth of the wind error from the 12Z run, the growth of the temperature from the 12Z run, and the growth of the temperature error from the 0Z run. And they're both increasing with time, but the wind at both 0Z and 12Z is increasing faster. These are, of course, incommensurable units. I'm comparing meters per second in Kelvin, but what I'm looking at more is the slope of these curves, and the wind speed error basically spins up very quickly. 73% of the 12-hour wind error already exists by hour 3, okay? And the wind speed and the temperature error spins up faster at 12Z than at 0Z, and I think that makes sense because usually at 0Z you're sort of getting late in the day, the sun is going down, and there's basically the temperature's just sort of like declining, whereas there's going to be more error starting from 12Z because that's later mid-morning and you're getting into the convective boundary layer time. So here's a quick summary. The background wind and temperature biases appear in the HRB boundary layer forecast. Positive wind biases, they occur pretty quickly. They reach a peak at 600 meters at 0Z and 250 meters at 12Z. 1/3 of the bias is there in the first hour, 70% within the first 3 hours. The temperature biases are there also. They spin up more slowly, but they're manifested as excessively reduced stability. I've only looked at December and January so far, and I do not appear to be fooling myself. So that's all. So thanks for the opportunity to present this to you. Yes?
So you're mentioning for the temperature bias that it seems to kind of, at least evolve to kind of, around within the first 6 to 12 hours, that's when it kind of really manifests itself, and then have you looked beyond the first 12 hours if it's kind of just mostly stagnant?
You mean as far as temperature is concerned?
Yeah, like
Yeah.
the lowest level, kind of right near the surface.
Yeah, so actually I can go back to those plots that I showed earlier because that was emphasizing basically the 12, 24, and 36-hour forecasts. And so for the last part I was looking at, well, what's going on in the first 12 hours, okay? So basically for 0Z, this was, well, sorry.
No worries.
Okay, so this is relative to the analysis, which is similar to what I was showing at the end. So this is the error after 12 hours, the error after 12 hours, the error after 24 hours, and the error after 36 hours. Actually, notice the sign is going back and forth, okay? The largest temperature bias, verifying at 0Z near the surface, actually occurs in the first 12 hours. Then it backs off, and then it gets worse again. But the reason is because these alternating times are starting at either 0Z or 12Z. So that was that slide that I kind of glossed by, okay?
Yeah, I was kind of curious about that since I was trying to do some plots myself about temperature biases relative to meteor stations. And I was also kind of using the January period, kind of looking at 18th analyses of the compared to meteors, and I also kind of noticed that the bias was kind of grew from mostly negligible bias around the initialization time to more pronounced bias around 6 hour lead time, which I think was mostly warm bias for most components. And then it kind of became mostly stagnated after 6 to 9 hours, so it seems to be kind of consistent with what you're showing.
Okay, that's good. We can talk about that a little more. I think that the two things that are involved here is starting at different times within the diurnal cycle are likely to be more conducive to error. Okay, so if you start in the morning at the beginning of the solar heating, you're more likely to sort of make mistakes than if you're starting around 0Z and you're sort of like just gliding down in that the temperature cooling off with time. But the other thing we're starting with is it may be that there's something about the initialization, so that runs started at 0Z and 12Z are fundamentally different. One's maybe starting off a little better, one's stumbling out of the gate a little bit, okay? And I think that's the kind of thing that's showing up here. Yeah,
Is there anything you know about the formulation and design of the boundary layer parameterizations that would explain some of this behavior?
Yeah, so that's what I'm thinking about now. So the question is, does this tell me something about the boundary layer scheme? So the MYNN is a TKE scheme. The knock on TKE schemes in the past has been they don't produce enough mixing in the convective boundary layer. That's actually would be manifested by a lapse rate that is too steep, okay? Maybe the difference in mixing between momentum and temperature is gonna help me explain this. But I think the best thing for me to do now is to try to reproduce some of these simulations, focusing on the 12 hours so I could basically pull out the HER boundary layer scheme and try other boundary layer schemes which have many different assumptions and characteristics, and maybe from that I'm going to be able to tease together what is it about this scheme, which is pretty good, but it could certainly be better. Okay, Andrew?
I was curious, you may not have a large enough sample size yet, but subsetting any of these sort of errors based on the ambient weather conditions at the time of launch, in terms of it being sort of a low overcast, high overcast, clear sky conditions, precipitation, seeing if there's any differences across that.
I think there's a lot we can do with it. What this is being limited by now is, as you said, sort of the sample size.
Yeah.
And the reason is because, as I said, I don't think these data are being archived anywhere. Maybe Esril is archiving them, it would be nice, but the next step I'm gonna do is contact them and see if they can, if they're keeping some of these simulations, because I'm basically gathering roughly 37 gigabytes a day of HER files, which in 2 days disappear forever from the server, okay? So, so that's why, actually I would much rather be analyzing June, July, and August than September and January, but eventually I'll be able to do that as well. Any other questions? Okay, so if you have any feedback or suggestions on how I can evolve this work or something, please feel free to come talk to me, and thanks Lance for the opportunity to present this to you.
Thank you, Rob. What are the forecast implications while we're change here, do you think?
Well, I think the forecast implications of if this also occurs in the same way in the warm season is you are basically getting systematic errors in Cape, okay, and SIN, and
Also some shear. Also
and shear.
Yeah.
Hey Lance, did you want to postpone the UberJet stuff to next week, given the
Yeah, why don't we do that?
We could do that.
Yeah. So why don't we just close the, we'll do the UberJet next week, and then we'll close on the Lizard. You guys take over? Yeah.
I guess the one in the P1.
I didn't realize it got to be 5 minutes.
Well, it gives me time. I'll run some of the same diagnostics on this past week in the meantime too, so I can even bolster it further. I've got so far too. Exactly. Yeah.
Entertain the kids with jets next week.
Exactly right.
Oh, I'm still messing around.
Alright, so to close off the map, to get toward the end of map discussion, we'll briefly discuss the upcoming weather this weekend in the upper Midwest, and then Danny will talk about the severe weather potential in the south, and the Great Plains as well. So, real briefly, picking up where Lance left off, actually let's step this back a little bit more, maybe turn on archive mode on Tomer's maps there. We don't need to go very far back. Let's just step back a couple time steps here on the Q vector map here. So this is Q vector divergence at 700 hectopascals. In red is representing Q vector convergence. Blue is Q vector divergence. So here's the trough that Lance was talking about that brought snow to Arizona and over into California. And as we go forward, this trough is going to progress eastward out into the Central Plains. And as it progresses eastward, we're expecting it to produce a deep, or pretty rapidly deepening cyclone. And then you can see here as the surface maps do reflect, there's a cyclone over here over Kansas, and then as this moves up forward, up toward Iowa, Minnesota, and the rest of the upper Midwest, you have a lot of Q vector convergence, so you have a lot of support for ascent here. And overlapping here in the precipitable water map, you can just line up the two. So really where you have a lot of forcing for ascent
from QG and as analyzed by the Q vectors, you have a lot of moisture in place as well. So that could set up a pretty interesting precipitation event, which also Dan will talk about further south. And this moisture is really being pulled out of the Gulf, and I think if we had a little bit of a big or a larger scale view, perhaps some of the Pacific moisture is tapped as well and is coming up. And let's step forward as the cyclone strengthens and moves up into Minnesota, where a snowstorm will progress. Let's just go one more step back, actually. So here you can see there perhaps is a little bit of a moisture source out of the Pacific, and also coming up here out of the Gulf. The Gulf is opened up, and you have the moisture transferred all the way up into Wisconsin, and the moisture starts to wrap around the cyclone, and really up through Minnesota and parts of Wisconsin is where you could perhaps get some blizzard conditions this weekend. And also, there's also some freezing rain and sleet expected south of there as well. So I think Danny will next talk about the severe weather potential in the south. So.
Yeah, I'll get, pretty well then, probably 500 winds there, and then vorticity on the right-hand side. Yeah, so as this trough deepens, it's really beginning to become negatively tilted, and with the fairly short wavelength, there's going to be a lot of forcing for ascent as it tracks northward. But if we just look at some of the severe weather parameters, there are some fairly significant ingredients here for a severe weather outbreak in the southern Mississippi Valley, mainly Arkansas through eastern Kentucky, maybe up into Kentucky, and then western Tennessee into northwest Mississippi. So just looking at some of the initial parameters, with this trough and strong ridge in the south, in the southeast, a strong trough approaching in, you have really strong wind shear over the central Mississippi Valley here, northeastern Arkansas, northwestern Mississippi, and western Tennessee. If we go to vorticity on one of the other maps, one thing that we do notice is that especially in the upper levels, there is not, especially right in this area where the severe weather threat is, there's not a ton of ascent in the upper levels, but there is a lot of ascent in the lower levels as this front moves through. So we go to, I guess, tomorrow at 21Z. Yeah, I'll notice that the bulk of the vorticity advection is going to be, it's actually going to be off this map and up towards the Midwest where your cyclone is. But if we look into this area, there's going to be some forcing for ascent in the mid-levels. And if we go to 850 vertical velocity, and then go back to, I guess, 18Z tomorrow's good. A lot of your forcing for ascent is right along this front here, which suggests you might have more of a linear mode to some of the convection, and there is a little bit of ascent, especially as you get into parts of western Mississippi, which does suggest there might be a slight risk for seeing more discrete supercell and convection out ahead of that squall line. And just the role of how that convection evolves over time, that might play a result in the exact mode of the convection, whether you have more of a damaging wind risk with an organized line, or you have more of a tornado risk with any discrete or semi-discrete convective elements in that line along or ahead of the front. So if we look at some of the severe other parameters, we go to surface-based CAPE. So going out to, I guess, 18Z again, you tend to notice that there's a little bit of, between looking at all the models, there's a little bit of some uncertainty into how much cloud cover there is tomorrow, which will play into a role of how much instability can develop, especially across as you get further north into this eastern Arkansas and western Tennessee area. A key role in that will be the amount of convection that sort of develops, sort of associated with that warm convection tonight, overnight, and into early tomorrow morning. So depending on how much convection there is tomorrow, you can that will determine on exactly how far north this instability can develop tomorrow, whether it gets into southwest Tennessee or even further north into southwest Kentucky as the night goes on. But just looking at the overall structure, there's going to be about 1,000 joules per kilogram of Cape. It looks like a little bit more or less depending on the exact amount of cloud cover, with some of your best values sort of in eastern Arkansas and northwestern Mississippi. So if we go to the SBC page, yeah, if you pull up the day 2 convective outlook, yeah, you've got basically sort of what we've been outlining is the highest risk is right over the Mississippi Valley region, right into eastern Arkansas, northwestern Mississippi, and western Tennessee. And that is associated with that main risk for damaging winds, with the potential for more tornadic activity, especially depending on the amount of discrete convection that can materialize. Just one thing to talk about the tornadic activity. I guess can we pull up HREF here, and then maybe go back to pivotal weather and pull up a sounding for somewhere. Yeah, that's good. So if we look at the sounding here, and this is one of the reasons why we're concerned about the tornadic potential in especially discrete convection, or even in any linear convection, if you can get some mesovortices embedded in any squall line here. Because we have low LCLs, really strong shear, especially in the low levels with helicity above 300 meters squared per second squared, and low level shear around 40 knots in the 0 to 1 kilometer layer. Directional shear, especially once you get above, once you get around maybe 3 to 6 kilometers, it's a little bit uniform in this layer, which may have a role in just the amount of discrete convection that can develop. But looking at some of just the overall potential, as I mentioned before, the amount of forcing that develops will also play a role in exactly how much discrete convection there is. So if we go into pulling it all together and looking at the, let's just go into the fixed layer, significant parameter, just the mean. And just as the overview of some averaging, a lot of the high-res ensembles like the high-res NAM, the ARW, and the NMM models, you can see that some of the best parameters are right in this area where south of the warm front, and in that area where you have some of your stronger shear values, and you have the instability as well. Just looking a little bit more into what some of the high-res models have. If we go into the storm attributes, let's look at the 4-hour max updraft velocity, see what some of the high-res models are depicting for as we go into tomorrow evening. So out into about probably 22, or as we get into the early afternoon. And what we see is that a lot of the high-res models sort of are showing what we sort of already analyzed synoptically, which are that you might have some stronger velocity tracks right in the northwest Mississippi into eastern Tennessee area. And again, that's sort of dependent on storm mode, with also sort of mesovortices embedded in any squall lines. So putting it all together, I think the SPC risk area for tomorrow looks fairly good with the potential for tornadic activity and damaging squall line in the Mississippi Valley area right there. Just overview, personally, I think that as you get into more northern areas, I think a squall line and a little messier convection is a little bit possible with slightly more discrete values of convection as you get closer to Mississippi and south, as you have a little bit less forcing for ascent, especially in the low levels, which might help keep things a little bit more discrete. So one other thing that we sort of touched on before, the amount of flooding that has been going on in this area might be an issue as well, with the amount of precipitable water and moisture that's coming up with this system. you're going to have some issues of flooding as well, especially just with the amount of rain that's fallen over this area for the last few days. I think we can go to precipitation and see what, probably 24-hour mean. Yeah, so this area, right, and as you get into northern Mississippi and parts of Tennessee, they've already had upwards of 5 to 10 inches of rain over the past few days, and another 3 to 5 inches of rain on top of that is not going to be good for some of those areas that are already underwater there. And lastly, just one thing to mention, as the cyclone intensifies going into the Great Lakes and moves northeastward into the weekend, it looks like there could be a fairly significant wind event here in the Northeast, especially, we'll get into it here in Albany some, but especially in western New York, it looks like there could be, you just go to mean sea level pressure winds. Yeah, right here. Yeah, as we get into, yes, the cyclone sort of starts to occlude and it moves off to the northeast. As we get into some of this northwesterly flow on the backside, there could be some probably 40 to 50 mile per hour gusts as we get into the latter portions of the weekend. So that'll be just something to keep an eye on now for if there are any localized power outages in the northeast to come then. But I think that's about all I have for this system.
Thanks, Danny. One question. Does anybody know, is there an algorithm, for example, if you have very wet soils, less wind is needed to topple a tree than if it's dry soil? So the question is, do the power companies need to worry about this, given all the saturated soils that are down there in part of the Ohio and Tennessee Valley?
Yeah, definitely. I think so basically there's some sort of competing factors there. On one hand, you do have all those wet soils, but another thing is, since we're still in February and I don't think they're quite getting the leaf
There are
out
no
there,
leaves
even though it
yet,
has
but,
been, even though it has been fairly warm down there the past couple of weeks.
But there are a lot of southern pine trees.
Yeah, the leaves aren't quite on the trees for all the deciduous trees on there, so that might be part of a saving grace. But I do expect, especially if there's a squalling sort of, this northern Mississippi to western Tennessee, there will be a risk for a lot of power outage or down trees and stuff there.
Hi. Any other questions? All right, well, thanks to everybody. We'll reconvene next Friday.